Welcome to the video, guys. In this video we're going to discuss about electrodes. Electrodes is a second chapter of electrochemistry, and previous lesson we learned about conductivity. In our syllabus there are 4 electrodes. We'll be learning about that in this video. I'll be including every important points. Please don't forget to take notes. I hope you're ready. Let's hop into the video. Before learning about electrons in equilibrium, we should learn about the reactivity of metals in a solution. Reactivity of metals in solution. For example, if we place a metal in a solution, I'll take magnesium. Magnesium in aqueous solution, it is in solid state and they form Mg2 plus ions, aqueous, and 2 electrons. Magnesium rod is dipped in the magnesium 2 plus solution. There will be quick buildup in electrons on the magnesium. The magnesium rod will be surrounded by the solution of positive magnesium 2 plus ions, and some of the magnesium 2 plus ions will reclaim their electrons and stick back to the magnesium rod we dipped into the solution. Mg2 plus aqueous solution plus 2 electrons, and they form magnesium solid. In our syllabus there are 4 types of electrodes. What is electrode? Electrode means that a system is a system where a metal is in dynamic equilibrium with its ions. A system where a metal is in dynamic equilibrium with its ions. System where a metal is in dynamic equilibrium with its ions. In our syllabus we have 4 types of electrodes. The first electrode, metal and metal ion electrode, and the second one is metal insoluble salt electrode, and the third one is gas electrode, and the fourth one is redox electrode. In an electron there could be only in one electrode there could be only 2 reactions. One, it can attract release electron. 2, it can attract electron. Now let's look at an example. There are 2 electrodes. One electrode is made up of magnesium and the second electrode is made up of copper. If we consider those, Mg solid forms Mg2 plus 2 electrons, and if we consider Cu solid, they form copper 2 plus and 2 electrons. And these are the reaction that could occur. This is a reversible reaction. This is reaction number 1 and this is reaction number 2. Here one metal will undergo reduction and other metal will undergo oxidation. In this case, the first reaction, the forward reaction is oxidation reaction, and the second one is reduction reaction. Oxidation means releasing electron. Reduction means gaining electron. To find the potential of an electrode, we use a reference electrode, which is we called as standard hydrogen electrode. We compare the electrode with another electrode. We use standard hydrogen electrode to compare other electrode with. Okay, let's write it down. Each electrode has different electrode potential. Here we compare the electrode potential with standard hydrogen electrode. Standard hydrogen electrode. And standard electron hydrogen is used in some conditions. The conditions are conditions 1 atm pressure, and it should be the temperature should be 25 degrees Celsius. Temperature should be 25 degrees Celsius. And the concentration of the hydrogen ion, H plus concentration should be 1 mole dm minus 3. Now let's look at standard hydrogen electrode. This is a solution. This is dipped in the solution, dipped inside a solution, and there will be an equilibrium established between the hydrogen gas and H plus ions by there will be a equilibrium established by the hydrogen molecules and hydrogen ions in the solution, which is catalyzed by the platinum. This is PT, and there will be H plus equals here. Concentration will be 1 mole dm minus 3, and here H2 gas is inserted, and this is a PT wire. Now let's see how we measure the potential of a electrode using standard hydrogen electrode. Let's draw the cell. Okay, this is the structure, and this is magnesium strip, and this is dipped into a solution. These are dipped into the solution, and this is PT, and this is PT wire, and these are conducting wires, and here the H2 gas is inserted, H2 gas, and this will be a voltmeter, and in this solution there will be magnesium 2 plus ions equals, and here there will be H plus equals, which is 1 mole dm minus 3, and this is salt bridge. I'll explain what is salt bridge. We use salt bridge to complete the circuit. We use salt bridge to complete the circuit, which acts as a liquid junction, which forms a liquid junction. And also the salt bridge is just a glass tube filled with a solution such as potassium nitrite. Let's write it down. Glass tube filled with solutions or solution of an electrolyte. It is filled with solution of electrolyte, solution of electrolyte such as potassium nitrate, potassium nitrate. 1 and 2. These are points of salt bridge. And each side of the electrodes are called as half cell. And okay, we will show which is half cell. Okay, if we consider this is a half cell. And if we consider this one is also a half cell. And there is another point in the salt bridge, the content in the salt bridge. And the electrolyte used in salt bridge does not react with salt bridge. The compound which used to form salt bridge doesn't react with either contents in the beaker. How the potential of the electrodes are found? Here they consider the standard potential, standard hydrogen electrodes potential as 0 voltage, and they are connected, and the voltmeter reading will show the electrode potential of the metal. In this case, the reading will be the potential of magnesium. The voltage reading means it is potential different, potential of the, hydrogen minus potential of magnesium, and that's how the electrodes potential are found. This standard hydrogen electrode is considered as 0 volts at 1 atm pressure and 25 degrees Celsius and 1 mole Tm minus 3. For example, if we take the above cell, this electrode and this electrode, the voltmeter reading is, example, 2.37 volts, and the voltmeter shows the reading of magnesium as negative electrode and hydrogen as the positive electrode, and therefore the magnesium and magnesium 2 plus and magnesium electrode is recorded as minus 2.37. Here the magnesium has higher ability to form ions than the hydrogen, therefore it is minus electrode, negative electrode. The magnesium 2 plus aqueous over magnesium solid, the electrode potential is minus 2.37 volts. One of the electron will undergo reduction and other electron undergo oxidation, and here the magnesium 2 plus undergo reduction because it has the ability to attract electron more than the hydrogen. Now let's see how the electron notations are written. Electrode notations. Electrode notation: Pt solid and a dash interface and H2 gas, and it forms H plus aqueous, and these are this line. Vertical line shows the interface between Pt and H2 gas, and this interface shows interface between H2 gas and H plus gas. For example, if we write notation for magnesium, let's write notation for magnesium. Magnesium solid, and there will be an interface magnesium 2 plus aqueous, and that's all. There is no any other interfaces. And the next part we're going to look at is metal insoluble salt. Let's look at metal insoluble salts, or which we call as calamine and silver chloride, silver chloride electrode. Metal and insoluble salt electrode, we call it as, there is two electrodes, calamine electrode and silver chloride. Metal insoluble salt electrode. What is metal and insoluble salt electrode? If a metal is in contact with a solid salt of the same metal, such electrodes are called as metal insoluble salt electrodes. So let's write it down. If a metal is in contact with the solid state, solid salt, solid salt of the same metal, is called as metal insoluble salt electrode. Example for these are calamine electrode and silver chloride electrode. In these electrodes, a saturated solution of KCl is used for electrical conductance. Let's write it down. In these electrodes, a saturated solution of KCl is used for electrical conductance, and there will be a PTY also. PT wire is used to establish the electrical conductance. Establish the electrical connection. Now let's draw a diagram for calamine electrode and silver chloride electrode. Here, let's draw calamine electrode. Here, let's draw silver chloride electrode. This is the calamine electrode, and this is the silver chloride electrode. Let's identify the parts. This is a PT wire, platinum wire, and this is a PT electrode. This is the PT electrode. PT electrode, and this in the green color thing is KCl solution. KCl solution. This is saturated KCl solution. Saturated KCl solution. This is also KCl solution. And this one is Ag metal, silver chloride. This is and this part is used to connect the second cell. Used to connect second cell. And this blue color part, this one is mercury liquid, Hg liquid. And this part, red dots present, and that part is called as calomel paste. Calomel paste. Calomel paste means Hg2Cl2. This is mercury liquid, and this is calomel paste, which is Hg2Cl2. And the tip of the part is called as separator. Tip of the part, mark here, separator. This is calomel paste, and this is mercury liquid, and this is separator. The separator is used to connect the second cell. And the solution of the calomel electrode and AgCl electrode is saturated KCl solution. Okay, this wire in silver chloride, we use the wire, it is silver wire, Ag wire, and here the electrode is silver chloride salt on silver wire. AgCl salt on silver wire. This part at the bottom, this part is ceramic or quartz, glass fiber. Just it's a junction. Ceramic, quartz, fiber, glass fiber. Junction. And this part is used to connect the cell with the external solution. I'll write it here. Used to connect the cell with, electrode with external solution. In metal ions, we learned that the standard hydrogen electrode is a reference electrode, and we can, in general, the calomel electrode and silver chloride electrode are also known as reference electrodes, as the potential of these electrodes remain almost constant during the experiment time. Their potential is constant during the experiment time. Here we use PT wire. and here we use Ag wire. The solutions are same, saturated KCl solution. And here we use PT electrode, and here we use Ag silver chloride on silver wire. We use that as the electrode. Here we use separator. Here we have a junction, and there is a calomel paste here. The reaction in silver chloride electrode is AgCl solid plus electron. They form Ag plus, sorry, Ag solid plus Cl minus aqueous. The next part we have is gas electrode. Gas electrode. In our syllabus, we have two electrodes. First, hydrogen electrode. Hydrogen electrode, we already learned that. And the next one is chloride electrode. Chloride electrode. This hydrogen electrode is called as standard hydrogen electrode. We know that. Standard hydrogen electrode, and its potential is 0 voltage. Let's look at the reaction. 2H plus aqueous plus 2 electrons. The reversible reaction, they form H2 gas. And now let's look at the chloride electrode. It's supposed to be chlorine electrode. And now let's look at the chlorine electrode. Chlorine is a well-known oxidizing agent. It acts as oxidizing agent. It undergoes reduction. And let's look at the reaction. Cl2 gas plus 2 electrons, they form Cl2 gas. Cl2, 2 electrodes, and they form Cl2 gas. Condition should be same. Here 1 mole Dm minus 3, 25 degrees Celsius, 1 atm. Here also it should be 1 mole Dm minus 3. Also they have only mentioned the concentration. If you write the notation for chloride electron, the notation will be Pt solid and chloride gas and Cl minus aqueous. Last electrode is redox electrodes. Both oxidized and reduced species are present in that electrode solution. Redox electrode, let's write it down. Both oxidized and reduced species must be presented in a solution of electrode is called as redox electrode. Here we use, as usual, we use PT wire, platinum wire, for electrical for electrical connection with the external circuit. Now let's look at a iron redox electrode. Iron redox electrode Fe2 plus and Fe3 plus redox electrode. Fe3 plus is reduced to Fe2 plus. Is a reversible reaction. How these electrodes are created? These electrodes are the platinum electrode can be inserted into a beaker containing a solution of both iron Fe2 plus and Fe3 plus ions. The concentration should be 1 mole Dm minus 3 with respect to each other and couple this to a hydrogen electrode. Let's draw this electrode. Let's draw a redox electrode. This is the Fe2 plus Fe3 plus redox electrode. In this solution, we have Fe2 plus, Fe3 plus solution, which contain Fe3 plus and Fe2 plus. They will be in aqueous form. Here, this one is a PT wire, and this one is a inert metallic electrode. Inert metallic electrode, which is platinum or platinum and palladium. Okay, now let's write the notation. There is few rules in electro notation. The first rule is phase boundaries. Phase boundaries are separated by a vertical line. And the second rule is physical states must be included next to each chemical species if given. Species and condition also should be included. And conditions must be included. For example, let's take a gas electrode. In the gas electrode, there will be PT solid and separated by vertical line, which is the interface, and O2 gas and OH minus aqueous. These are interfaces mentioned. And now let's consider a redox reaction for the second one. Redox electrode, PT solid interface and Fe2 plus, which is aqueous, and the conditions are 1 mole Dm minus 3, whole 3 in bracket, aqueous, 1 mole Dm minus 3 interface Fe3 plus aqueous and 1 mole Dm minus 3. If the temperature or atmospheric pressure are given, you should also mention that those. Okay, now let's summarize the type of different electrodes with types of different electrodes with their types of electrodes, standard notation, redox couple, and reduction half reaction. First electrode is metal and metal ion electrode. Metal and metal ion electrode. Standard notation can be written as, if we consider the metal in a interface, Mn plus is aqueous, and the redox couple is solid, metal solid and metal ion. The half reaction, reduction half reaction is M metal ion plus aqueous plus number in electrons into M solid. And the second electrode is metal insoluble, metal and insoluble salts is M metal solid interface Mx N solid and X minus ion aqueous. And the redox couple is metal solid and salt solid. And the redox reaction is the reduction half reaction is Mx solid plus electron. It forms n number of metal solid plus X minus aqueous. The third electrode is gas electrode. In a gas electrode, there will be a Pt solid interface and X2 gas interface X plus aqueous, and it will form the redox couple is X2 gas X aqueous, and the redox reaction X plus aqueous plus electron, they form half X2 gas. The last electrode is redox electrode. Redox electrode. Redox electrode's notation is Pt solid interface M plus ion aqueous and M2 plus ion aqueous. The redox couple is M plus aqueous M2 plus aqueous. M2 plus aqueous plus electron, they form M plus aqueous. This is the reduction half react. I mark these red lines as to separate them. Take a screenshot if you want. When we are writing the electrode reaction, it should be represented in one single error. Let's consider potassium. If potassium is there, K plus aqueous plus electron is the reduction reaction. They form solid, potassium solid, and this will be represented in single arrow. This means there is a current flowing through. Single arrow means there is a current flowing through. Now let's consider the standard reduction potential of elements, electrodes. When when the potential is more negative, the reduction ability increases. Reducing ability increases, undergo oxidation. When the potential is more negative, oxidizing ability increases and they undergo reduction. Let's look at an example. If we consider potassium, there is a potassium solid and potassium ion electrode, and there is a zinc solid and the zinc 2 plus electrode. The potential of the reduction potential of potassium is minus 2.93 volts and zinc's reduction potential is minus 0.73 volts. If we compare these, which is more negative? More negative means this is more negative, which means it undergo oxidization. Undergo oxidization. More negative means they undergo oxidization, and therefore the zinc will undergo reduction if these both are, if the cell contain potassium electrode and zinc electrode. This will be the reaction. Potassium will undergo oxidization and zinc will undergo reduction reaction. Oxidization means they release electron, reduction means they gain electron. More negative means they already have more electrons. Negative means electron has a negative charge. Just an example, they already have more electrons. Therefore, the negative potential will try to oxidize, and the positive ones have less electrons, low number of electrons. Therefore, it will gain electrons. More negative means oxidization. More positive means reduction. And that's all for electrodes. I hope you guys understood. Thanks for watching.